recording has started. So, to get us started for today, we're going to actually look at something a little bit different. At the top of your outline, there are 3 pictures. And those pictures show you different states of matter: solid, liquid, gas. And I'm sure from the time you've talked, my daughter is in kindergarten and they're starting to talk about what solids and liquids and gases and stuff like that. But we've learned some general properties of solids and liquids and gases. Take a couple seconds, talk to the person next to you, and list a couple of things that you know about what makes something a solid, what makes something a liquid, what makes something a gas. So talk to the person next to you, list a couple of general things about those 3 types of matter, then we'll come back and discuss. Go. All right, so let's discuss. Let's start off with solid. What do you guys talk about as far as solids go? What are some of the general properties or things you know about solids that you discussed in your little group? Come on, you were all talking. Nick, go ahead.
They hold their shape.
Okay, so we say that they have a definite shape, or they hold their shape, regardless of where we put them, right? That's going to be, the shape of that solid is going to remain the same. What else? What else do you know about solids? How is that a hand or?
Yeah.
Good.
Molecules and the solid.
Okay, that the particles that make it up, I'm going to go with particles, and we'll see why in just a second, okay? The particles that make it up have very little movement, okay? That they don't move much at all. It's really more of a vibration, right? They just kind of like shake back and forth, but they're pretty much stuck in place, right? What else? What else about a solid? Anything else we want to talk about? Jeremy, go ahead.
Definite volume.
Definite volume. Along with its definite shape, it has a definite volume, meaning that whatever container we put it in, whether it's a small bowl or a big box or a big room, it's just going to stay the same size. That doesn't affect that substance. Anything else we need to throw in there? That pretty much covers it, I think. Okay. All right, let's go to the other end of the spectrum, right? Let's talk about gases. What are some things you talked about with gases in your small little groups?
It does not have a definite volume.
Okay, so no definite volume, meaning that whatever container we put it in, right, Andy, what is that gas going to do?
It's just going to spread out.
It's going to spread out and fill up the container, right? It's going to spread out as far as it can go, right? What else? We can build off of that, right? I'm going to take the obvious stuff first, right? It has no definite volume, but it also has no definite shape, right? That whatever shape container we put it in, it will fill up that container as well. Volume and shape, right? What else? Eris, go ahead.
The atoms in it move around a lot.
Okay, I'm going to go, Eris, instead of atoms, I'm going to go more generally with particles, because we could be talking about single atoms if we're talking about like a noble gas, neon or argon or something like that. But we could be talking about molecules if we're talking about like carbon dioxide or oxygen or something like that, right? Does that make sense, the distinction between those? Okay. So I'm going to go generally with particles, right? But more specifically though, more importantly, what do those particles do?
They move around.
Okay, they move a lot, right? A lot of movement. What's also one thing that allows them to move a lot? Mark, good.
They're really spread out.
They're really spread out so that there is a lot of space between it. So a lot of space between, that's a W, particles. Whereas solids, the particles are very, very close together. In gases, those particles are very spread out. A lot of space between them, okay? Do we have to go into liquid, or can we sort of make the connections, right? Well, real quick, right? What do we know about a liquid? Andy, go ahead.
It takes the shape of the container.
Takes the shape of the container, right? But what else, though? Does it necessarily fill that container?
No.
Not necessarily, right? You can have a half full glass of water, right? So it takes the shape of the container. It has no definite shape, but it does have a definite volume, right? Did you want to throw something else in there, or is that what you were saying? Okay. Anything else we got to put in there? We should probably, fill and make the connection here, make the bridge, right? If solids have not very much movement and gases have a whole bunch of movement, right? How much movement do particles in a liquid have? Logically, it would be, somewhere in the middle, right? So the movement of particles less than gases, but more than solids, right? Does that make sense? All right, good there? All right, now that we got those things taken care of, those are going to be important reference points that we're going to come back to as we start talking about the different properties of things that are covalent bonds, things that are ionic bonds. We'll find out that based on the type of bond, we're going to see those type of bonds fall into these sort of categories. That most things that have ionic bonds fall into a certain category, most things that have nonpolar covalent bonds fall in this category, blah, 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 blah. Okay? Good there. All right. So let's get to the outline here. All right. The physical properties of a substance are affected by the attractive force between the particles. The attractive forces between the particles. We talked earlier that a chemical bond is an attractive force between atoms. It's an attractive force that holds atoms together. In this case here, we're not talking about the bond. We're talking about the attractive forces once the bond is already formed. As an example, here's a magnet, right? And this magnet has a north pole and a south pole. This magnet might represent a chemical bond because, right, one side of it, the other side of it, they're holding each other together. Does that make sense? What we're going to talk about today isn't so much the north pole and the south pole of this magnet being attracted to each other and holding each other together. We're going to be talking more about what happens when the north pole of this magnet and the south pole of this magnet come together. So now we're not talking about a single magnet, we're talking about like multiple magnets. Does that make sense? It's not the attractive force that holds atoms together, it's the attractive force that holds molecules together or particles together. Okay? So keep that in mind, right? That statement is not the same as your definition of a chemical bond from the very beginning of this unit. The greater the attraction between the molecules, the more energy is required to overcome those attractive forces. And a lot of times that results in an increased melting point and an increased boiling point. Looking at those properties of solids, liquids, and gases, right? We talked about that solids have the least amount of movement And gases have the most amount of movement of the particles. Why? Because the particles in a solid attract each other very strongly, and they don't allow the other particles to move very much. But in a gas, there's almost no attraction between the particles, and that allows them to spread out as much as possible. So these attractive forces within a bond can also then lead to the attractive forces between the particles once those things are bonded. Good there? All right, first thing we're going to talk about. Oh. Is that part? Do you have a blank there? Okay, never mind. We'll get to that later. All right. Structure of an ionic solid. First, if it's an ionic solid, right, it's going to be held together by ionic bonds. So let's take one that you're pretty familiar with, sodium chloride. Knowing what you know about naming elements and getting formulas and stuff like that, right? If you have something that's sodium chloride, that means it has sodium in it, and that means it has chlorine in it. And if you look on the periodic table, you find that sodium is in the first column, right? Or group 1, it's an alkali metal, so it has a charge of +1, or it will form a charge of +1. Chlorine's a halogen, group 17, -1, and that means when they come together, the formula for sodium chloride is NaCl. And I think a lot of you probably knew that already. Okay? That's salt, right? What we refer to as salt. This is what's on your table at home or when you go to a restaurant or whatever. And I think most of us probably knew that already. But let's look more at what it looks like. What we find out is that in an ionic solid, any ionic solid, it works for sodium chloride, but it works for any other ionic solid. Aluminum chloride, potassium chloride, calcium chloride, we find the same thing, that these ionic compounds will form a three-dimensional network called a crystal, or sometimes we will refer to them as a crystal lattice. And it happens because each ion is attracted to multiple ions of the opposite charge. So here's what happens. Here is sodium, and it's +1 charge. And then here is chlorine, and it's -1 charge. And those two would be attracted to each other. So I'm going to make them a group because they're attracted to one another. And then somewhere else, another sodium and another chlorine are attracted to one another. And then somewhere else, another chlorine and another sodium are attracted to one another. And then somewhere else, this chlorine and this sodium are attracted to one another. Good there? Okay. But what happens is this. While this sodium and this chlorine are attracted to one another, this chlorine has a negative charge. And yes, it's attracted to this positive charge, but it's attracted to all the other positive charges that are out there as well. So, if this group of sodium and chlorine come together and come closer to this group of sodium and chlorine, while yes, this chlorine here is attracted to this sodium, it's also attracted to this sodium. Why? Because they're both positive charges. Yeah, 1 plus, 1 minus, but that doesn't mean this chlorine loses its negative charge. It will be attracted to all the other positive charges that are out there as well. And then, let's say this one comes along, and we're going to flip it this way. This one comes along here. Oh, look at that. There's another positive charge, and it's attracted to this negative charge. And let's say this one comes around, right? And we'll flip it around this way. Yeah, it's upside down, but well, let's not do that. Let's go this way. That now this positive sodium is attracted to this negative chlorine, and that's true. But if this one comes around, guess what? This positive sodium that was attracted to this chlorine is also attracted to this chlorine. Why? Because it's -2. Remember we said, I told you at the beginning, we're not just talking about one magnet. We're talking about the interaction between different magnets. Okay? So now, we started with one sodium attached to one chlorine, and that was great. But now, because of all the attraction of all the different charges that are out there, we've ended up with this big interconnected network. And what we find out is that it's real difficult to say that this chlorine is attached to this sodium. They're all connected to one another in a big three-dimensional network. And if we keep doing this, we would keep adding positives onto negatives and negatives onto positives, and eventually we would end up with this picture right here, where you have a whole bunch of positives attached to a whole bunch of negatives. Okay? This structure here is what we call a crystal, or a crystal lattice. It's not just one sodium attached to one chlorine. It's one sodium surrounded by a bunch of chlorines, and then that chlorine then surrounded by a bunch of sodiums, and vice versa, and along down the road. Okay? Good with that? At least the idea of what a crystal is. So what does that then mean? We refer to this crystal being held together by interionic forces, right? Because we know English, we know that inter means between, right? Yes. Yeah. And if it's interionic, that means between ions. So, right? Interionic forces are due to the attraction of oppositely charged ions. There is a greater attraction between ions of greater charge. So, in sodium chloride, where sodium has a +1 and chlorine has a -1, there's a strong attraction. But if you do something like calcium oxide, where calcium has a +2 charge and oxygen has a -2 charge, guess what? Those are going to be attracted to each other even more strongly than sodium and chlorine are attracted to one another, because they're bigger charges. Interionic forces are the strongest forces that we're going to feel out there between particles once they have formed bonds. Yikes. So interionic forces are our strongest forces between particles. They are held together most tightly of anything that's out there. And what does that mean? That means that compounds that have ionic bonds, where the ions are held together in a crystal lattice, this crystal formation, we're going to see a general set of properties. First, ionic compounds have very high melting and very high boiling points. That means generally they are solids at room temperature. Why? Because we said solids don't allow the particles to move very much. This very strong attraction between all these ions prevents one specific ion from moving hardly at all. It just sits in that spot, in its spot in the crystal, along with all the other ions. Many of them are soluble in water. Later on in chemistry, you'll talk about the solubility process, or the process of dissolving. And you'll see that ions play a very important part in that. If we could make this ionic compound a liquid, if we heat it up high enough that we get it to melt, what we find out is that it becomes a very good conductor of electricity because of the ions that are there. In a solid form, those ions can't move very much, but in a liquid form, they move a lot, and that allows charges to flow real easily. Just like we talked about a conductor back in the electricity unit, right? Anything that allows electrons to flow nice and evenly makes it a good conductor. That's the case with this as well. Okay? Good there. So we'll see that these general properties show up for things that are ionic compounds. Why? Because they're held together so tightly, doesn't allow the other things to move. All right. Solids, poor conductors of electricity. So if you take your salt shaker at home and just hook up a battery to two sides of it, you won't see any charge flow through that. But if you could somehow melt that salt, which you can't do at home because you don't have anything that's hot enough, you would find that electricity flows through that melted salt, which is pretty hot. So I don't recommend you do that. So. All right. What we find out is that there are certain types of molecules that don't have, that aren't ionic compounds that actually are very strong, like this. Okay, diamond, right? Are we aware of diamond? Yeah, diamond is our hardest substance out there. Blah blah blah, all that good stuff, right? Okay. Diamond is actually made of a bunch of carbon atoms, but the way that these carbon atoms are put together, right? They're all connected to one another. That makes them very, very strong. Quartz is silicon dioxide, if I remember correctly. And they're all interconnected, right? Look at all these lines connecting all of these molecules together, all these atoms together. And that makes them very, very strong. Very hard to break, very hard to separate. And that makes them solids at room temperature generally. All right. What we find out, though, is that atoms that are held together with covalent compounds have a very different set of properties. Atoms that are held together with covalent bonds, the compounds that they make up, generally have lower melting points than our ionic compounds. What we find out is that they won't conduct electricity regardless of whether they are solids or whether they are liquids or whether they're dissolved in water or whatever. And we'll find out that some of these compounds, these covalently bonded compounds, will behave differently when they're mixed with other substances than our ionic compounds do. That some of them will dissolve in things that ionic compounds won't. Ionic compounds will dissolve in things that some of these covalent compounds won't. Right? Different kinds of bonds, different kinds of properties. And why is that? Well, it has to do with the fact of sharing those electrons versus the complete transfer of those electrons. First, non-polar covalent bond. Review, right? What makes a bond non-polar? Harris, go ahead.
The electrons are both shared by each atom equally.
Right, that we have an equal sharing or an equal distribution of electrons. Harris, what are we going to see about atoms that have non-polar covalent bonds? What property do we look at to determine the polarity? Do you remember? Electronegativity. So things that are non-polar are going to be things that have, how will their electronegativities compare to each other? Equal or pretty close, right? They don't have to be exactly equal, but they have to be pretty close, okay? We said there was a little range where the difference can be between 0 and 0.4. That if we see that range there, we'll generally classify that as a non-polar covalent bond, okay? All right. Similar attraction for electrons, so that shared pair is evenly distributed. And that means that there are no sides of that molecule that behave differently from other sides, right? In this magnet, the North Pole side and the South Pole side behave differently from one another. There's no such thing in a nonpolar covalent bond. It's like this cardboard box. It doesn't really matter what side you show me, that we point to this magnet, or if we point that side of the box to the magnet, doesn't do anything because there's no difference between the sides. Nonpolar covalent bond, right? Good there? I didn't have anything fill in right there, did I? What that means is that, remember when we drew this picture here, right? There's a lot of attraction here. This sodium ion is attracted to this chlorine ion and this chlorine ion, and this chlorine ion is attracted to this sodium and this sodium and this sodium, right? When we have a nonpolar covalent bond, there's just no attraction between those particles. There's nothing to hold them together. These two magnets are attracted to each other because of the north and south poles, and we can line them up. But if I take these two sides of the cardboard box, right? Nothing. This is like a nonpolar molecule. There's just nothing to hold it together. And so there's no attraction for them. What does that mean? What that means is that nonpolar compounds, or compounds that are held together with nonpolar bonds, have very low melting points and boiling points. Many of them are gases at room temperature. We talked on Friday about a certain type of molecule that is always nonpolar. Do we remember a certain type of molecule that's always nonpolar? We talked about it the first day. We talked about covalent bonding. What was the first covalent bond I showed you? You remember? Talk about diatomic molecules, right? Diatomic molecules are always nonpolar bonds. Why? Because the two atoms being the same means that they both want electrons exactly the same way. Here are a couple of diatomic molecules. Hydrogen, oxygen, nitrogen. What else? Chlorine. Okay, there's more, but those are the four I put up there. Hydrogen, oxygen, nitrogen. Know anything about those and how they come in the real world? What does oxygen come in, state of matter in the real world? It's a gas, right? Because there's nothing to hold those oxygen molecules together. Nonpolar molecules won't conduct electricity no matter what you do to them. Whether you dissolve them, whether you turn them into liquid, whether you turn them into gases, they just don't conduct electricity at all. And they will only dissolve in liquids with similar molecular polarity, like dissolves light. You're going to talk about that more when you talk about dissolving in chemistry class. Okay? Good there? So that leaves us then with those molecules that are polar. So when we talk about things that are polar, right? Differences in electronegativity values. When these atoms form covalent bonds, the electrons will be not shared evenly. We call this a polar covalent bond. So again, we're looking at differences in electronegativity. And we said that here, if we have differences between 0.4 and 1.7, those bonds will then be classified as polar. When we have other side of the molecule. For example, we get a picture that starts looking kind of like this. Notice, first we have these funny shapes, I guess we should go with that, okay? Where one side is bigger than the other side. Notice the bigger side has the minus charge on it, right? We talked about that if we talk about the shaded area around that nucleus, the bigger area represents a greater attraction, or a greater probability of electrons. So in a polar molecule, because one side wants electrons more than the other side, there's a greater probability of finding electrons on the bigger side than there is on the smaller side. That means this side has a higher electronegativity, whereas this side has a lower electronegativity, right? Greater probability of electrons on one side than there is on the other side. And it makes this molecule look a lot like this magnet, where one side is different than the other side. And it makes the one side behave differently than the other side. Okay? Properties-wise, where are we here? That leads to something that we call a dipole force. Dipole forces, these polar molecules are attracted to each other via the quote-unquote negative end, right? The bigger side of this molecule is quotation marks negative, right? That's what it says up on the board. It's not like an anion. It's not like that circle that I drew up on the board before, where we have a distinctly positive part and distinctly negative part. It's more like that magnet, where one side is different than the other side, even though they're part of the same compound. It's not as strong as the interionic force that we talked about earlier. But it's stronger than the almost non-existent forces that exist between non-polar compounds. So, that leads us to some differences. Okay? Polar molecules will attract each other slightly, whereas nonpolar molecules have no attraction for one another. And that means polar compounds are a little bit harder to separate. And that means that they're going to have a little bit higher melting points. Not as high as ionic compounds, but somewhere in the middle. They still won't dissolve stuff, they still won't conduct electricity. They'll dissolve in certain things, maybe things that are different than the ionic compounds, but they will dissolve in certain stuff. All right, good there? The hydrogen bonding part's at the end. We'll just skip over that, okay? That's something that we don't have to talk about. It's something I kind of added in there. It's nice to kind of know about, but we won't worry about that right now, okay? All right, so there's our properties. Tomorrow, you are going to see this in action. So probably a good idea to bring this outline with you, so once you've taken your data, you can answer questions based on the things that we talked about today. Tonight, I'm going to give you your quiz, so work on your quiz tonight. A lot of the things we talked about with polar, ionic, nonpolar, polar, that will show up on your quiz as well. Okay? Bring that back tomorrow completed.